So, all right, the squeeze theorem. Squeeze theorem said, let's look at the wording, and then I want to, this kind of, as many things are in calculus, I would call this a picture theorem. A picture, that cliche that picture's worth 1,000 words or something, it's true in calculus. A lot of times we can summarize these existence theorems with a picture. And it tells the whole story much more eloquently than all the symbols and words do. But let's look at this here. Suppose the functions f, g, and h have the property that for all x in an open interval containing c, except possibly at c. So you can tell we're talking about limits here, right? Because we don't really care what's happening at c, but every place else, it is true that the value of f of x is less than or equal to the value of g of x, and the value of g of x is less than or equal to the value of h of x. What we really should say there is g of x is greater than or equal to f of x and less than or equal to h of x. What's that imply? These are output values. What's that imply then? If we think about this in terms of like a vertical order of these functions on this interval, describe that in simpler terms. What's that mean? Which function sits on top? H of x sits on top. Which function sits on the bottom? F of x. And which function is squeezed in the middle? Okay, g of x, right? So if that's true, then, and also one other caveat here, if the limit of the bracketing functions, by bracketing I mean the bottom and the top, if the limit of both of the bracketing functions as x approaches c is equal to L, then what do you think must be true of the limit of g of x? If g of x is squeezed in between those two and both of their limits approach L as x approaches c, what do you think must be true of g of x? Got to be the same thing, doesn't it? It has to have the same limit. And you can see this with a picture, I think, more easily. Let's do that. There we go. How about that? Okay. So again, would you agree here that every place except possibly at c, g of x, the value of g of x is greater than or equal to the blue f of x function and less than or equal to the, what is that? That's, what color is that? No, there's a name for that. What do you call that one? What is it? Magenta. That's it. It's magenta. The magenta h of x function. And if the limits of f of x and h of x converge on the value L, then g of x is squeezed to that same limit, isn't it? Okay, everybody see that? Okay. All right, so this is, when you see the picture, it's pretty obvious, right? But it becomes useful. It becomes useful in some instances. Let's look at one like this. Like, we're going to use the squeeze theorem to find the value of this limit. Okay, well, what happens? What do we always try to do with limits first? Plug it in. We're going to evaluate directly. So if we do that, if we plug in 0, we've got problems, right? Because the function isn't even defined at 0, is it? Right? We get sine of 1 over 0, which is, that's not allowed. Okay, so what could we do here? Well, there's some stuff we could do. One thing we could do is we could recall here that the sine of, as long as x is not equal to 0, the output of sine has to be pinched between -1 and 1 inclusive, right? In other words, the smallest value that a sine could output would be -1. The biggest value it could output would be +1, right? Sine function just wiggles between those two y values forever, right? Okay, so if that's true, then, oops. we could say something like that, right? How come? You remember why? Why can we make that statement? This goes back to, we talked about this a couple years ago. You probably talked about it last year too a little bit. What's a property like if we have an absolute value of something is less than a number? Remember, that's always equivalent to the compound inequality, right? Whatever's inside the absolute value bars is going to be constrained to sit in between the negative and positive values of the outside number, right? Okay, is that ringing a bell? That relationship? That's a pattern that we see with, with absolute value inequalities. And it kind of makes sense, doesn't it? Because if the absolute value of u in this case is less than the number a, then that means that the kind of the magnitude of that number, positive or negative, has to be small. Has to be less than a, doesn't it? Right? Everybody get that? Okay. Okay, so we've made this little change here. Okay. I'm going to show you a better way to do this too, by the way. This is the way our book goes through and shows it. And this is pretty common for textbooks to see it this way, but there's a little easier way to finesse our way through this when we're all done. So what if we multiply both sides by the absolute value of x? Okay, we could do that, right? We've got this inequality, the absolute value of x, and absolute value is a positive number. Okay, so I can multiply both sides of an inequality by a positive number and preserve the direction of the inequality. What happens if I multiply both sides of an inequality by a negative number? Got to flip the inequality, don't we? Right? Then that in that case we'd flip the inequality. But because we're multiplying by an absolute value, we're fine. Okay. So that gives us something like that then, right? Okay. And we're just following some algebra steps here. Okay. So far, so good? We just took this inequality, multiplied both sides by the absolute value of x. Well, what's our motivation for doing that? Well, it's this, right? We could use this same principle we just used up here if oh, by the way, if I multiply two absolute values together, little property here, you guys tell me what's the absolute value of A times the absolute value of B equal to? What do you think? What's the magnitude of that going to be? Absolute value of, oops. What do you think? Try it with some numbers. You try with a variety of numbers, like the absolute value of 3 times the absolute value of 4 is 12, right? What's the absolute value of negative 3 times the absolute value of positive 4? 12. What's the absolute value of negative 3 times the absolute value of negative 4? Okay. Yeah. So it's equal to the absolute value of the product of those things, right? Because no matter what, the absolute value is going to make that product positive, right? Everybody get that now? Does that make sense intuitively? Okay. So then that means that we could lump all this stuff into one absolute value, right? Okay. So that takes us here. Then the absolute value of that product, x times the sine of 1 over x, is less than or equal to x. Okay, well, then we can go back and use this property, right? We know that whatever's inside this absolute value inequality is going to have to get pinched in the middle, and it's going to be greater than the opposite of what's outside, okay, which would be negative the absolute value of x, and less than, or equal to in this case, we've got an equal sign, the positive value that's outside, which is the absolute value of x. Okay, well, then, come on, there we go. Okay, then what's that tell us? Okay, well, By the squeeze theorem here. What is the limit of the red function, negative the absolute value of x as x approaches 0? What is that? If I just evaluate that directly, what do I get? 0, right? No big deal. What is the limit of the positive absolute value of x as x approaches 0? 0. Okay, but look what we had here. X times the sine of 1 over x is always, for all values of x that are not 0, right? It's always guaranteed to be greater than or equal to the red function and less than or equal to the green function, right? Well, if those outside bracketing functions, if their limits converge on the value 0, then by the squeeze theorem, doesn't the limit of the blue function get squeezed to that same value, right? So we got it. The limit of the blue function is equal to 0. Okay. Now we involved a lot of absolute values in there, and that was okay. That's fine. But we could have maybe done this a little bit easier, I think. Okay, we could have said, all right, if we start with this original function up here, then we know that the sine of anything, right off the bat, the sine of any value is going to have to, the output is going to oscillate between -1 and 1, right? So that tells us that we could jump right to this part right here, couldn't we? Right? Because if we know that that value is going to oscillate between -1 and 1, if I multiply that by x, then that's going to oscillate between -x and x, right? Now, if x is positive, that's fine. Then negative x would be on the left and positive x would be on the right. But if x is indeed negative, that's where we need those absolute value signs in there, right? Because that controls this and makes sure that that red number is negative and the green number is positive, regardless of the sign of x. Okay, so I think you could just jump immediately down to this statement right here. Okay, and then from there, everything's the same. Okay, give me 1 to 5 on that. I mean, that's, again, calculus. Okay, that's pretty good, honestly. I mean, that's when you first see things like this, a lot of times it's just a lot to hold on to, right? It's a lot to. Calculus is probably the first class, I bet, where you're ever going to look at this stuff, and the expectation is probably that you don't just get it immediately. The steps are big enough now that you really got to think about this stuff a little bit. They're large chunks, but you get them. You just have to let your brain kind of stew over it a little bit and connect the dots. And it takes a little bit though. Sometimes it takes a little thinking. And I think I told you the story. Did I tell you a story about Andy having to stare at a problem for 4 hours? Did I tell you that one? God, I mean, that's normal. That happened to me in college. I don't know if it was exactly 4 hours, but I went through similar experiences routinely. I mean, math starts to get to a point where the steps just aren't so small that it becomes a significant enough and complex enough process that you really got to focus and let your brain digest and come back to it. And a lot of times that's important to do. Unrelated, but as you move to the next level in college, that's really an important thing to do sometimes, is let yourself take a break. Like, if you can stare at something, and I don't know how many times this happened to me, and this is some of the best advice I can give to young students, is when you get to the point where you're getting frustrated, a lot of times you just got to go away and do something completely different. Go out and play, I don't know, you play badminton or something, go do something that's unrelated to math. And as soon as you stop consciously trying to focus on it, how many times have you done this before where you're just like, oh, I got it? I'll tell you what I used to do. This sounds a little dorky, but when I was studying for finals and I was going through some really tough physics stuff, which involved a lot of really tough math, I'd get frustrated. I'd be studying and I would take some keys in my hand and I would take a little nap. I would let myself fall asleep, and as soon as I'd fall asleep and the keys would fall out and they'd wake me up, I swear it works like a lot of the time. It's like when you wake up, you're like, oh man, okay, I got it. I know how to proceed with this problem. And before I had no idea, I was getting frustrated. I wasn't thinking straight, and just getting away from it, even from a short period of time, and kind of letting your guard down. Man, that was a great trick for me. Maybe I'm a weirdo, but that one worked for me. Try that one in college. Maybe try it this year. I don't know. Let's look at one more example like this and see if you guys can kind of talk me through this one a little bit. How could we do this one? What was kind of the trick? I mean, what did we do here that was helpful before? Right? We took into account a property of a sine function. Cosine works the same way, right? So what could we do here? Do you know something? Is there a bounded value that you can tell me about? What is? You're right. The cosine, right? Cosine of something, doesn't matter what it is, right? The cosine of any number, of any input, is going to always be pinched between -1 and 1, isn't it, right? Okay, now notice x is approaching 0. So x could never be 0 here, right? Because we can't divide by 0, but we don't care. For every other value other than 0, that cosine function is defined, and the output value is going to be greater than or equal to -1 and less than or equal to +1, right? So there's a good step. So this stuff right here, we know that cosine of 1 over x is going to be greater than or equal to -1 and less than or equal to +1. As long as x is not equal to 0, which is fine. Doesn't have to be. We're just taking a limit. Okay, so then how could we go one step further? What about 1 minus that cosine function then? What would its values be pinched between? Everything in the purple box. Let's make that a box. Yeah, everybody agree? Does that make sense? Okay, because if the cosine function is going to be constrained to be greater than or equal to -1 and less than or equal to +1, what would 1 minus that be? Right? That's 1 minus the very smallest value cosine function could have is -1. What's 1 minus -1? 2. The biggest value cosine could have is 1. What would 1 minus 1 be? Okay, right. You see what I'm saying? Okay, so the purple part then is going to be pinched in between. That's going to be pinched in between 0 and +2, right? Okay, well, what about the x then? Okay, well, we know that whatever x is, x times 0 is going to be 0, x times 2 is going to be 2x, right? Everybody agree? Okay. Now, we don't know if x is positive or negative, though, so we're going to make it positive by saying the absolute value of x. Okay? So we know then that the absolute, 0 times the absolute value of x is going to be less than or equal to the absolute value of x times 1 minus cosine 1 over x. And if I multiply this guy times the absolute value of x, that's going to stay on top, right? Okay, good. Right. Okay, well, as x approaches 0 then, what value is this limit going to go to? 0. Yeah, right. What's that limit going to go to? 0. So this one must go to 0, right? Everybody agree? Okay, so let's look at this. Okay, we know up here right? Okay, so that means that the function in the middle must also get pinched down to 0, okay? We've got those absolute values in there though, okay? Well, if you tell me if the limit of 0 times the absolute value of x as x approaches 0 is going to 0, what's the limit of 0 times x going to be? Right? If the absolute value is of x, say it again. What would it be? Again, let me say that again. I got to give you a chance to think about this. If the limit of 0 times the absolute value of x as x approaches 0 is 0, then you tell me what's the limit of just 0 times x as x approaches 0? Yeah, it's still 0, isn't it? Has to be, right? Has to be. And if if the limit of 2 times the absolute value of x as x approaches 0 is 0, then by the same reasoning, what's the limit of 2x as x approaches 0? Yeah, it's still going to be 0, isn't it? Right? And if, as we just showed by the squeeze theorem, the limit of the absolute value of x times 1 minus cosine of 1 over x as x approaches 0 is 0, then you guys tell me what's the limit of plain old x without the absolute values, x times 1 minus cosine of 1 over x as x approaches 0. What's that equal to? 0. Yeah, so we just proved it. There's our answer. It's 0. Okay. Now that's I think that's a step up conceptually. This is a kind of a proof-based look at calculus, right? Where we're not just solving problems, we're having to do a little proof here when you use the squeeze theorem, which is more college level stuff, but it's good to see it. Okay. Is this something that shows up a ton on like the AP test? No, not at all. It's not a big deal. I mean, it's nothing would ever be any harder than that at the very most. I mean, usually they're pretty, and you'll see this when we look at practice tests at the end. You'll see that the squeeze theorem, the way it enters into the AP test, is not that big a deal. It's really not. Okay, I'm going to let that marinate a little bit. Do you have any questions? Or what's that? How they? Well, I mean, really, they came up with it. You guys could have come up with it. You really could have. You come up with it just by that picture. Kind of is how you come up with it, right? The idea is that if you've got this limit that's undefined at C, but if you've got this consistent behavior where the black function whose limit is undefined is pinched in between these other two bracketing functions whose limits are known, then you must know what the limit of the middle function is. It's really very clever. It's not, I mean, when you look at that picture, you think, oh yeah, it kind of makes sense, doesn't it? I mean, it gets squeezed to the black limit gets squeezed to the same limits as the magenta and cyan. I think that's cyan. And cyan function, right? Okay. All right. I'll let this marinate, let you guys work on it, unless you have a specific question about this. More than likely, I bet you you're just thinking, okay, I just got to think about this some more and maybe look at some problems. So I'm going to let you do that. It's a short assignment.